Morning and welcome back. This is section 2 of chapter 5. In this section, we're going to be looking at what's called a definite integral. A definite integral is actually exactly the same thing that we were looking at yesterday. At least the part of it we're doing today is we'll be approximating a definite integral, and we do that by using rectangles. And those are actually called Riemann sums. So today we're going to see vocab, we're going to see notation, we're going to see how to do some on the calculator, and a couple properties, but there's really not much difference between today and what we did last time. And so, first question is, what is the definite integral? That's just the area under the curve. Same thing we were finding before. The official definition looks like this. A couple things we have here. We have the notation. This notation, this tells us we're going to be finding the area under the curve. It's actually the kind of a fancy looking S. It stands for the sum because it's a sum of rectangles. And then we have a beginning point and an ending point. That would be the beginning point and the ending point. And then the function that we're dealing with was f of x. Those are the y values of the rectangles. And then d of x, dx, that's the width of the rectangle. So if we're looking at a graph, we could make rectangles. So this would be A, that's the beginning, B, and then we have a few rectangles, however many it is. The height here is f of x. And then this width is dx. And so what the sum is looking at is we have f of x times dx. The I is the index. It just takes it from this one to this one to this one to this one to however many we have. Going from I equals 1 to n, we're going up to the n number of rectangles, and it's the limit as n goes to infinity. If we're looking at just this space, the more rectangles we put in there, what happens is they get skinnier and skinnier and skinnier until, for all intents and purposes, it's a line and there's no overlap or undercoverage. It's going to be perfectly on that. And that's the dx. It's the difference of x. It's the same from the same dx as when we were finding the derivative. Start out with the difference of x at delta x, but it's a really tiny difference. But this is the notation. That's all it does. So we're going to approximate using Riemann sums. To do that, it's the same thing that we were doing. It's just you won't have a table or a graph as much today. It's going to be more equations. But if we wanted to approximate from 1 to 9 of, let's just say x squared dx, and then using 4 intervals, we would first want to figure out the width of the interval. We did this in the last section. We're going from 1 to 9, that's 8. 4 intervals, so that means 8 divided by 4 is 2. Each of them is going to be 2 long. Oh, and let's find the right-hand rectangles. So if they're each going to be 2 long, the very first thing that we're going to have is after 2 is going to be 3, so we're going to have f of 3. That's 3 squared times the width of the rectangle, which is 2, plus next one, is 5 squared times 2 plus 7 squared times 2 plus 9 squared times 2. We just need to square it, multiply by 2. In these cases, since everything's multiplied by 2, I would actually factor it out. We're going to have 2 and then just times 3 squared, that's 9, plus 25, plus 49, plus 81, and then we just add them together, multiply by 2. 130, 155, 164 times 2 is going to be 328, I believe. So that's the same thing. Yeah, last time we were just putting these numbers into a table. You could still make that table if you want. You don't have to, but you can. There's absolutely nothing wrong with finding the values, putting them into a table, and then going. Especially if the question has you do like the left, the right, the midpoint. Like if you have to do a couple things, if you put them into the table, the numbers are there and ready for you, so you don't have to think about finding them a few times. Using a calculator to approximate an integral. The calculator is going to become more and more useful in the next few chapters. There are times when it is appropriate to use a calculator to approximate. There are times when it is not. On tests, you'll have times when you can use a calculator, times when you cannot use a calculator. It's important to be able to do these by hand, but sometimes it's not going to be something that you can do by hand possibly, or maybe you would be able to do it by hand, but it's going to be a very excruciating process, or involve so many random decimals, irrational numbers that you would end up using a calculator anyway. So we'll see how to find the integral using a calculator, the definite integral. If we want to approximate from 1 to 9, x minus 3x squared, using a calculator, there are two methods we could do this. The first one involves using a graph. So very first thing, we would graph it, just like we would graph anything else. Make sure that the whole graph that we're looking at from 1 to 9 is on the viewing window. That is very important for this. And then you'd go to the calculate menu. We've gone there before. We've seen things like values, zeros, minimums, maximums, intersects. Down at the bottom, we have the derivative, and then the last one is the definite integral. And notice it even has the same notation that we're using. So you'd click that, and if you've got one of the newer calculators, well, actually, this one, it's fine. You click that, it's going to ask for lower bound and upper bound. So you give it 1, enter, 9, enter. It'll shade it for you so you can see what it's looking at, and it gives you the integral. This is 74.666667. To me, that looks a lot like 74 2/3. The other method does not involve graphing. But what would you do in your home screen? Go to the math button, the math menu. We've been here before. That's where you change things from fractions to decimals, numbers where you have absolute value. Down at the bottom, we have the numeric derivative. Remember, we could find the derivative at a certain point. And then Fn int, this is going to be the numeric integral. It's the definite integral, but approximated. And what this does is it finds a whole bunch of rectangles. It's literally what it does. And so it's not necessarily going to be perfect, but it will be close. But if we choose that, and here's where if you have a new calculator, it's going to pop up with the exact notation. Plug it in, make it look like what we're doing. If you have an older calculator, you have to use some calculator note, like the syntax where it's equation, comma, the lower bound, comma, the upper bound, comma, x, and it'll find it for you. But then you just hit enter, and we come out with the same thing. So 2 ways of using calculators. In the next chapter, you'll use them even more because the problems get bigger, and you're setting it up is actually the intent of those problems. This chapter, unless it tells you to use a calculator, I would probably not. And then the meaning of the definite integral. The definite integral is the total change over the time frame or the interval that we're looking at. Remember, the derivative was the rate of change. This one's the total change. Yesterday or last time you had a problem involving an elevator that was going up and down. We had the velocity of the elevator at certain times, and we had time. When you found the integral, you could find something like, let's say, over the first 60 seconds, it was 7. That means that in those 60 seconds, it has gone up 7 feet. The total change was 7. It may have gone up and down and up and down, but at the end of the 60 seconds, it ended up 7 feet higher than it was when it started. In that problem, it said it started at 40 feet. So you're now at 47 feet. One of the things that can help you figure out what it's talking about is look at the units. Multiply the units of your x and y together and see what you get. That will help. In the exploration activity we did, there was the question about the football. We had cross section of areas. That was in inches squared times the length from the end of the ball, which was in inches. You multiply inches squared times inches, you get inches cubed. That's a volume. So that integral was talking about the volume. And if we took the whole thing, that would give us the volume of the football. Another thing with some of the meaning is we can go below the curve and get these negative spaces. Those are actually negative areas. It's possible to have a negative area under the curve, which I know your geometry teacher would be like have a cow if you gave a negative area. But in these, the negative area has meaning. For instance, back to the elevator problem. The positive area is when the elevator is going up. The negative area is when the elevator is going down. This one ends up at negative 7.58. If the elevator started at 40 feet, at the end of this time interval, it would be at 32.42-ish. We would subtract it when it ended up lower than it was when it started. So the negative is okay, and it has its own meaning. Some quick properties about the definite integral. If the bounds are the same, this is 0. Because if you remember the integral, we're finding by rectangles. What's the area of a rectangle? It has a height of something and a width of 0. Something times 0, which is 0. So if those two bounds are the same, it is defined to be 0. If you switch the bounds going from A to B, you switch from B to A, it just becomes negative. That's all that happens. One way you could think about it is the x values switch directions. So instead of going from like 1 to 3, you're going from 3 to 1. That's a negative direction. So it becomes negative. So that allows you to switch in case you have to. And there are some questions that come up where switching them is wise. And the last one, if you have a constant and you're taking the integral of a constant, it's that constant times the difference. And what that is if you have a constant, remember the graph of a constant is just a horizontal line. If we're looking from A to B, that is actually a rectangle. You don't have to estimate the area under that curve. You can just find the area under that curve. And so it's height, that h, times this distance, which was the b minus a, which is exactly what it has. Um, and so that is, those are some properties about the definite integral. Next section, we will look to see how we can find these using calculus as opposed to finding a bunch of areas, because finding a bunch of areas gets a bit tedious. The calculus is actually easier. So uh, until next time, keep working problems, keep asking questions, and as always, happy mathing.